So here we have air entering a turbojet engine at these conditions. Okay, and the inlet velocity is given as 1000 kilometer per hour. So that's equivalent to 278 meter per second. The pressure ratio across the compressor is 8. So we're talking about the pressure at the exit of the compressor, P2, divided by the pressure at the entry of the compressor. That's P1. So P2 by P1 is 8. Okay. The turbine inlet temperature, T3, is given as 1200 Kelvin. And the pressure at the nozzle exit, so that's P5, right? The pressure at the nozzle exit, it's given as 0.8 bar. So of course, pressure at state A is equal to pressure at state 5 because it's a constant pressure process, constant pressure heat rejection process. The work developed by the turbine is equals the compressor work input. So this another thing is given. So what we're saying is, as we discussed before, turbine work out is equal to compressor work in. That is H3 minus H4 is equal to H2 minus H1. Okay, this is what we're saying in here. Now, given this information, we also have been provided that the diffuser, compressor, turbine, and nozzle, diffuser, compressor, turbine, and nozzle, which are all these processes right here. These processes are all isentropic, so that's what we see in the TS diagram as well. And there's no pressure drop for flow through the combustor. Excellent. So 2 to 3 is a constant pressure process, right? P2 is equal to P3. For operation at steady state, we need to determine the velocity of the nozzle exit. So we want V5. Okay, V5 is question. We need to determine V5 and also the pressure at each principal state. Now we can neglect kinetic energy except at the inlet and exit of the engine and neglect potential energy throughout. So we cannot, so we are saying VA is not equal to 0 and V5 is not equal to 0. So these are the velocities or the kinetic energies at the inlet of the engine and the exit of the engine. All other velocities are 0. So V1 is equal to V2 is equal to V3 is equal to V4. These are all 0. That's all. This is the information that's provided to us. Okay. Now we are pretty confident about solving Brayton cycle. So this is sort of similar to the Brayton cycle in a lot of sense. And with just 2 extra processes, we need to take into account the energy balance for diffuser and nozzle, and we should be able to solve for this. Okay, so the question that we are looking for is, well, we need to determine the velocity at nozzle exit. But before that, we also need to determine the pressure at each principal state, meaning we want pressure at P1, 2, 3, and 4. Okay, so given this, given the information that we just discussed, let's discuss how can we determine pressure at state 1. How do we get P1? Any ideas? Let me repeat the question. We have some information given for the entry point of the diffuser. Okay, the temperature, pressure, and the velocity are given. I need to determine pressure at state 1, P1. How do we determine that? What do you think would be the processes? How do we go about solving for that? Let me give you a hint. Here there is nothing mentioned about specific heat. So again, we're dealing with an ideal gas. So we're going to treat this to be an ideal gas with variable specific heats. So now I want to hear what is your strategy to go and determine P1?
Maybe we should start with energy balance and get H1. Then when we get H1, we go to the ideal gas table and get PR.
Perfect. And then what do we do with the PR?
Use it P1 over P2 is equal to PR1 over PR2.
Excellent. So Abdul Hamid explained to us what exactly we need to do, right? That's a simple process. And You guys have done this before for the Brayton cycle, and that's the thing that we need. So first of all, we have enough information given at state A, and we need to determine H1 first. So the procedure is we determine H1 by energy balance to the diffuser. Once you have H1, well, we will have PR1. And what do we do with PR1? Well, you see, A to 1 is an isentropic process. So P1 by PA is going to be equal to PR1 by PRA. Okay, we have PR1, we have PRA, we have PA. We get P1 directly. Okay, so this is the entire, these are the different steps that we're going to take one by one. So the first step certainly is to get H1 from the energy balance to the diffuser. So given the information at state A, that is the temperature at state A, first we go to table A22 and determine the enthalpy at A and the value of PRA. Okay, once you do that, then you apply energy balance on the diffuser. Okay, and when you apply energy balance to the diffuser, we said it's HA plus VA square by 2, right, is equal to H1 plus V1 square by 2. We said V1 is 0, right? The velocity at all other components are 0, except the velocity at A and velocity at 5. So this is the energy balance that we just discussed and derived for the diffuser. All right. So the only ways in which energy gets transferred here is through kinetic energy or through the enthalpy changes. Okay. So here we have HA, we have VA given. We need to determine H1. Okay. So here again, since this is a sort of conversion from joule per kilogram to kilojoule per kilogram, right? When we talk about using the velocities here, so we need to divide it by 1000. So what we do is H1 is equal to HA. This is the value that we have for HA plus V square by 2. Okay. So velocity is in meter per second. We need to, and when you square it, you're going to get it equivalent to joule per kilogram. Okay, the units that is. To convert that into kilojoule per kilogram, we divide it by 1000. That's what we are doing here. Now this is a very important part here. If you don't divide by 1000, you're going to get a crazy value. So this is one common area of students making mistakes. So once you have done that, we get the enthalpy at state 1. It's 278.7. Now with this value of enthalpy, we need to go back to table A22. Okay, we know that both enthalpy and PR1 are just functions of temperature. So using this value of enthalpy, we need to determine through interpolation what the value of PR1 is. Okay, and we get a PR1 of 1.07. Now, since the process A to 1 is an isentropic process, we know that the ratios of pressures would be equal to the ratios of relative pressures. So PA by P1 would be equal to PRA by PR1. PRA we already know because we know the temperature at state 1. Okay, this is the values right here. P1 we just calculated it. PR1, sorry, we calculated it. PA is given in the question. So it's a matter of plugging in the numbers here and writing in terms of P1. Okay, when you plug in all these numbers that we have, we get P1 of 1.34 bar. So you can see there is a pressure rise, of course, within the diffuser, not a very huge one. Okay, it increases by, let's say, about 0.5 bar. Any questions here? So the procedure that we have followed here is an important one because we're going to use this almost at every step to determine the other pressures. All right, we have P1 now. How do we determine P2? Well, P2 is sort of easy to determine because the pressure ratio across the compressor was given. P2 by P1 was given. So since P2 by P1 is given, we already calculated P1 and P2 comes out to be 10.78 bar. All right. So as you can see again, this is where the main pressure rise occurs. Of course, the diffuser also helps a little bit in the sense that it takes care of of a bit of the pressure rise that we need to reach P2 or the combustor pressure. So P2 is done. Now, before we go and talk about the other stuff, let's talk about the pressures for now. Okay, so we have PA, we have P1, we have P2. How do we get P3 then? What about 2 to 3? What sort of a process is that?
Equal to
Same
V2
pressure.
because it's
Exactly. 2 to 3, just like in the Brayton cycle, 2 to 3 is a constant pressure heat addition process. So P2 is simply equal to P3. You don't have to determine anything. Okay, so we have P3 right here. Now, once you have P3, right, we also have been provided with T3, so we can get S3 and PR3. Now, the question for us is to get uh, H4. All right, we need to determine H4, or sorry, we need to determine P4 as well. And basically, for us to determine P4, we need to sort of determine H4, just like the way we did for, let's say, state 1. And the simple reason why we want to determine H4 is because we said we want to determine P4, but for P4 we need H4. And the reason we need H4 is because once you have H4, then we will have PR4, and using PR4 and considering that 3 to 4 and 4 to 5 are both isentropic processes, we will be able to go back and determine P4. Okay, so the question is, how do we determine H4? Well, we're going to make use of the fact that the turbine work output is equal to the compressor work input, right? That I said was a good approximation, but that has been given in the question itself. So the compressor work input is H2 minus H1, and the turbine work output is H3 minus H4. Here we need to determine H4. Okay, S3 we already know, right? Because the temperature was given. H1 also we determined it through energy balance on the diffuser. Now the question is H2. We don't actually know H2, so we need to go and determine H2. And determining H2 is an interesting prospect. We're sort of going the opposite way. Now that we need H2, let's go back here and see what are we doing. We found P2. All right, we found P2. We have exact value for P2. Now 1 to 2 is also an isentropic process. Okay, so since 1 to 2 is an isentropic process, the ratio of pressures will be equal to the ratios of relative pressures. P2 by P1 is something that we know already. The ratio is known, and this will be equal to PR2 by PR1. Now, PR1 is something that we already determined it, right? When we were trying to find out the pressure at state 1. So in this equation, everything is known except PR2. So we can plug in the numbers and calculate PR2. Okay, PR2 comes out to be 8.56. And why do we need PR2 now? Well, we know that for an ideal gas, enthalpy, PR, and a lot of properties depend only on temperature. So once you have PR, you will be able to do interpolation from table A22 and get S2. And S2 is what we need to go ahead and calculate H4. Okay, so this is how we do. This is how we get H2 right here, simply by making use of again the ratios of pressures, equating the ratio of pressure to the ratio of relative pressures, and then using PR2 to interpolate. Okay, so we have H2 here. From here we have H2, H1 already what's calculated before. S3 is indirectly given in terms of the temperature at state 3. So by plugging in all these numbers here for the different enthalpies, we can get H4, and H4 comes out to be 1051 kilojoule per kilogram. Now what do we do with H4? Well, it's the same process. Once you have H4, go and determine PR4. Okay, so we go and determine PR4. It comes out to be 116 again from table A22 by interpolation. So as you can see, there's a lot of interpolation happening in here. Now we have PR4, and with PR4 we're going to again play the same trick, right? 3 to 4 again is an isentropic process, so P3 by P4 would be equal to PR3 by PR4. We know P3 exactly because it's equal to P2. We know PR3 because we know the temperature at state 3, and we already know PR4 just by determining the H4. Okay, so with all these known, the only thing unknown is P4, and when you plug in the numbers, P4 comes out to be 5.25 bar. All right, so now we have pressure at all the states that we needed, right? So P1, PA and P5 was given. PA is equal to P5. These were given. And then we found P1, then P2 is equal to P3. We found P2 as well. And we also found P4. So we have taken care of this part, right? The pressure at each principal state. We have sort of determined that. Now we need to go ahead and determine the velocity. Do we need any other information to go ahead and determine the velocity, or do we have everything that's needed?
We need
I
H5.
think
Yes, exactly. We need H5. And how can we get H5?
we know that P5 is equal to PA, and we know that from 4 to 5 is the isentropic process, so P4 over P5 is equal to PR4 over PR5. Then we
Excellent.
get.
Yes, that's exactly how we do. So you can see it's sort of you're using the same process everywhere, right? These are all isentropic processes, and you have to use exactly the same method. Excellent. So that's all what we start off with, right? We know P4, okay? We know P4, and we know H4. Now process 4 to 5 is again an isentropic process, so the ratios of pressures should be equal. That is, ratio of relative pressure should be equal to the ratios of pressures P4 and P5. PR4 we already know. We know P4, we know P5. Okay, from here we get PR5. And the reason we want to get PR5 is because we want to go back to table A22 and interpolate. So PR5 comes out to be 17.68, and through interpolation we get H5. H5 is 621.3. Now once you have H5, it's pretty straightforward. We already have H4 and we have H5, and this is where we apply the energy balance on the nozzle. Okay, and as we just discussed before, when you apply energy balance on the nozzle, well, H4 plus V4 squared by 2 is going to be equal to H5 plus V5 squared by 2. V4 is 0, so this term simply goes down to 0, and the velocity V5 is simply equal to square root of 2 times H4 minus H5. Again, here this is these are in kilojoule per kilogram. So to get the velocity in meter per second, we need to multiply this by 1000. Okay, and that's what we do here. So it's 2 times H4 minus H5 times 1000 to convert that into meter per second, and this is what we get, 927 meter per second. Now just to compare, the V5 that we got here is much higher than VA, right? VA was 278 meter per second, and the difference between V5 and VA is the thrust that is provided to the aircraft to move forward.